Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen. Welcome to the
Hello, everyone, and good morning or good evening or good afternoon, depending on where you're connecting from. Welcome to this online session, What is and Isn't an EMS? Define the line with Wärtsilä energy storage experts. A very much needed webinar, I think, to clarify a lot of doubts that I'm sure that everyone has. Thank you so much for joining today's session. My name is Cristina Galan from the ATA Insights team, and I have a couple of housekeeping rules before we officially begin the webinar, and then I'll pass it on to the Wärtsilä team. So before we start, just to let you know, the session is being recorded as we send the video, and we will send you the materials in a couple of days. If you are connecting from Zoom, you have a chat on the right, so let us know where you come from, your company, why you're interested in this topic, and if you have any specific questions during the webinar for our panelists, please use the Q&A box below, so we don't miss any of your questions. If you're connecting from YouTube, you also have a chat available for introducing yourselves and let us know a little bit about you and any questions that our technical team will pass on to our panelists. So I think we're finished here for our housekeeping rules. If you have any questions, please let us know. And I'm going to pass it to Luke. Luke, good morning. Thank you so much for joining us today and welcome.
Thanks, Christina. Let me start sharing my screen.
I'll stop sharing mine.
Yeah. The correct one there. Okay, good. Welcome today, everybody. We're still having a lot of people trickling in. It's our pleasure to get to spend some time with you, and I hope that we're able to everybody learn something and have a little bit of fun in the process. Today's topic, what is and isn't an EMS? The acronym stands for Energy Management System, first of all, and we have our own perspective from the Wärtsilä side. So just a brief introduction on ourselves. We are a global energy storage system focused group. The three panelists, myself, Scott, and Sunitha, are all in our energy storage and optimization business. And we have been delivering battery power plants at the utility scale around the world for over 15 years now. We have some pretty big projects these days. The scale has really exploded. And so getting a little bit into some of the features that we've been delivering to help with managing these plants at scale is part of the hope today. And the global footprint is hopefully able to connect with everybody since there's people joining from all around the world. Between the three of us, I lead the data science team here. And that includes battery health analytics, as well as forecasting and dispatch optimization. Sunitha leads our software solutions team. So advancing the platform standardization and the different things that are available off the shelf in terms of how all these different Lego pieces that make up an EMS, how do we actually put them together into a cohesive thing that makes sense to solve market-specific needs or specific groups of assets, and how they should be working together. And then Scott leads our integrated applications engineering team. So a little more on the customer-facing delivery side of the software group. And getting all of these advanced features, as well as off-the-shelf standardized things to work in the real world. So that little bit of background will hopefully be able to cover all of the wide range of software questions among this group. So the format for today, I have a couple of slides to kick it off with some definitions, talk about the purpose and the value that can be extracted from an EMS. And we're not going to use the term EMS a lot today. Part of our hope in this session is to almost avoid the term, to create a bit of a vernacular around subcomponents in a way that makes sense and is fresh for people. And then Scott, Sunitha will go next with some of the detail on some of the functionalities. And then Scott will close us out, and then we'll go to Q&A. So as we go, please be putting the Q&A questions into the Q&A section, and we'll be addressing those at the end, though. So as you think of them, please be sharing them with us. Okay, so let's try to define this first. Hopefully you're not a lost paramedic or first responder. EMS is an overloaded acronym already in our society. But so if you Google search energy management system, you get a lot of things. You get systems for residential applications or for the transmission system. You get microgrids, power plant control, things specific to batteries. But what's a BMS then, right? And is it running in the cloud, or is it running on a piece of hardware at the site, at the edge of the network of devices? Is it SCADA? Is it a data historian? Does it do forecasting or optimization? Does it do performance monitoring and analytics? There are so many things that fall under the umbrella of some EMSs that it can be a confusing topic, because we're not talking about the same thing, and we're not seeing eye to eye when we're trying to build a piece of an EMS, or when we're trying, if you're in the camp of people buying battery plants and software, if you're putting together an RFP, it can be very confusing what terms should or shouldn't be used. If something, I put this screenshot here, if something claims to do everything, it's highly unlikely to actually be able to do anything specific or meaningful. And I think that really resonates a lot with us. And at the same time, systems of systems often are able to produce something that no one system could do by itself. So this Aristotle quote, the whole is greater than the sum of its parts, is an important piece to not let go of. And then I put the Wikipedia definition. It's there as sort of the best definition I could find on the internet, because the definitions are so wide ranging. But in short, an EMS is a system of computer aided tools, software used by operators and electric utility grids to monitor, control, and optimize the performance of a generation or transmission system. And also it can be used in small scale systems like microgrids. Today, we're really going to focus on the battery as a battery power plant. So it falls into that bucket of generation assets. And there's a lot of data coming off of these plants that we want to make sure that they can be leveraged. So diving in a little bit, let's talk about components here, the physical equipment at a site There's high voltage equipment, transformers and switchgear. There's medium voltage equipment. Again, transformer switchgear, you've got some metering, preferably at least above the medium side, but there's also depicted a meter on the high side. That's also pretty common in our utility scale battery plants. You have what we refer to as the DC block, the actual container of batteries themselves, as well as the inverter. You also have a bunch of equipment referred to as the balance of plant, which is across both of these pieces of high voltage and medium voltage. And then you have generation assets themselves. And often batteries are co-located with other assets. There's existing infrastructure, a substation, a place to connect to the grid. And so there's often some other generation equipment reasonably nearby. But so then if we kind of take a step back and say, okay, that's the physical equipment, let's start diving into the software side. There are power plant control aspects too. So each one of these generation assets is going to have its own controller of some kind. And you can have a BESS controller, for example, that is from the battery vendor, but maybe it's not actually capable of all the things you need from a power plant controller. And you might need to do some kind of shared hybrid control logic there as well. That's an important piece of the puzzle. Meanwhile, there's dispatch signaling and data exchange with the substation that's happening for grid control. There's also data streaming from the plant up to the cloud. The reason that we need to get the data offsite is that these power plants are often in very remote locations. So the controllers have limited CPU and memory available to store all that data and computationally do something with it. And so when you get it offsite into the cloud, you can have a lot more availability to optimize your plant. You can have different interactions or commitments to the market. So energy traders might start to use that information in some way. You might aggregate multiple plants together that are not physically at one location. And then you might do different kinds of analytics. And so that is all of those different functions are normally not happening at site. And for those reasons I described. Meanwhile, there's sort of an off-taker who accepts bids and actually sends dispatch instructions. The dispatch instructions come through some kind of RTU at the site normally, depending on where you are globally. That may come back through some kind of cloud connection to the site as well. And then there's the asset owner itself, who will have their own various remote monitoring SCADA platforms or systems that they might need to do their job to remotely operate and maintain the plant. So there's a lot of things going on. And so this is my last slide before I hand it over to Sunitha. Let's chat a little bit before I hand it off of like, okay, so that's great. There's physical assets. There's sort of real world tangible purpose of all of those different pieces. But in our society, everything that's in a dark blue box is generally referred to in a lot of cases as the EMS. And that makes things very confusing because any one of these by themselves is probably not really an EMS, and everything together is really more of a software ecosystem than an EMS also. And so EMS is a little bit of a misleading term, and we find ourselves really not using it very much. It's the term we use for our software ecosystem and platform as a whole. Having a software ecosystem and a platform where all of these different pieces, the BESS controller and the plant controller, streaming millions of data points per minute off of the site up into the cloud for these large scale battery plants to do various cloud types of applications is really what the EMS space should be. And just reading through this list, there are different apps. So it's very common for us to have customers who buy some of these cloud apps, but not all of them. They don't necessarily have a purpose at a particular battery plant for, say, a renewable energy forecast or for some kind of optimization against a load curve or something like that. But then it doesn't mean that those functions aren't available or that they don't exist inside of the ecosystem or inside of the overall software context. And then meanwhile, doing things like remote operations and management and having a cohesive data collection strategy is really important. And so if you are in the space of owning multiple battery power plants and you have a BESS controller from multiple different battery vendors, which may or may not have some elements of plant control or cloud data analytics available, your operations team is stuck learning the different software platforms between different plants. They can't do certain functions in one or the other, and that they have to spend hours and days in training on how to use multiple different platforms and switching between the two. And so having a cohesive software strategy and an approach to minimize the amount of time that your operations team spends in training and in doing things, and that you have the state-of-the-art advanced analytics for battery anomaly detection and predictive maintenance of those assets, and the right kinds of alerting. So just-in-time text messages when there is a time-sensitive problem, but not getting flooded with text messages with a lot of alarms, and having the right kinds of software in place to have to leverage the advanced capabilities that my colleagues are going to go into of these battery power plants, which is part of that EMS ecosystem, is really important. If you don't stream the high resolution cell level data off of the site into the cloud to then do something appropriate with it, then you can't actually pinpoint problems and roll the right truck with the right equipment and the right spare parts at the right time. And you waste a lot of time with people at site mucking around trying to figure out what's going on. And so these kind of software platforms, which fit into the space of EMS, are really critical to ensuring that you're able to optimize what you're able to do with the battery. So the rest of this session is mostly focused on this space in the orange box. And so I'd like to hand it over to Sunitha to dive in a little bit with what kinds of control functions and advanced features we consider to be standard for this space of this part of the EMS. Sunitha?
Thanks, Luke. Good afternoon. Hello, everyone. So let's see what can an advanced BESS power plant controller can offer. So some of the key features are listed here on this slide, such as flexible and pluggable architecture, sophisticated power allocation algorithms, stacked power operations, multi-tenant site control, enabling batteries SOC calibration and cell balancing with automation, and so on and so forth. So what we are talking about here is the BESS power plant controller features, not just the BESS controller, where the given set point is forwarded to the inverters, for example. So when we are looking for a BESS power plant controller, we need to look for all these sophisticated features if it is supporting or not. So in the next slides, we will go dig into the little bit, take a closer look at each of or some of these key features. So architecture of a PPC should be able to support pluggable equipment drivers to communicate with various site equipment, to monitor, to collect the data, and to control as needed. So, and that data collected could be used for data analytics, reporting, warranty purposes, troubleshooting. Data is powerful. I mean, once we collect it and store it, and there are lots of uses for it. So basically with this structure, with this architecture, whenever we need to develop an equipment driver, we just write a driver, of course, using the protocol that equipment supports, and then plug it into the software configuration. And that data collected through these drivers could be exposed or published through different interfaces like HMI, SCADA, and API. And similarly, even as the market evolves, we would have to change or write the new power operations logic, and that needs to be plugged in as well into the site configuration. So a pluggable and flexible architecture of PPC would offer basically to make equipment integrations or the power operations integrations or any other application integrations, make it very easy to integrate and evolve. Next slide, please. So so we were talking about the sophisticated power allocation algorithms. So one such algorithm is like, which would balance the SOCs across all the site units. So what do we mean by that, right? I mean, this particular slide illustrates what a SOC balance-based algorithm or allocation algorithm will do. So while all the units are participating in plant's auto operation, the system keeps all its SOC within a similar range, of course, within an allowed dead band. And then as the units are operated, started operating in manual or manually operated, then these SOCs deviate. And as you can see from the top right corner screenshot there, the SOC deviates when the unit is manually operated. And once everything is put back into participating again into the plant's auto operation, the system tries to keep all the SOCs of the units into the similar range. So that as a result of this SOC balanced SOC algorithm, the units will keep in such similar range all its SOCs. So you can see that from the table there in the lower right corner, and then from SLD that all those units SOCs are kept in the similar range of SOCs there. Of course, within the allowed dead band of 2 or 3% within that. Next slide, please. So, sites may need to sometimes respond to, external signals while they are responding to external signals or set points from the external sources. They might also have to respond to the frequency changes that's happening locally. So in this case, both the frequency response operation as well as the external P signal operation should be combined to get a combined target P, and which could be the site output. But of course, we may have to apply some of the POI limits, transformer limits, or the battery limits on top of this combined target P, and before sending the the net set point to the inverters. So on the right-hand side, the dashboard screenshot, you see there is a portion of site output is coming from the frequency response, and portion is coming from the P set point from external source. And of course, also there is a voltage response, the Q set point from the voltage response there. So the point is, I think the ability to stack these power operations, multiple power operations, I mean, not just two, it could be multiple operations depending on which market you are. But the PPC should be able to stack and combine these power operations together is very critical for a sophisticated PPC. Next slide, please. So another advanced site control that some of the customers look for is like multi-tenant site control. What do we mean by that? So there is a large site, probably could be divided into multiple zones. like in this diagram we're showing that it's divided into 4 zones. And customer would like each zone participate its own market, or each of them in its own market, and all of them could be in different markets at the same time. So each zone providing the real power services for which it is in whichever market it is, while to meet the demand for the grid compliance rules to be at the plant level. So that means the demand to meet the grid compliance rules is calculated at the plant level, and that's intelligently distributed to the multiple zones to meet that demand. So this is one of the features that customers are looking for recently. And then there is yet another advanced and challenging and very important feature of a PPC is the enabling the batteries SOC's calibration and cell balancing with automation. So, as batteries are operated, the SOC estimation by BMS gets inaccurate, and those inaccurate SOC estimations can lead to the poor trading decisions, such as selling too much energy or too little energy, and which can result in decreased revenue for customers and also the suboptimal use of asset. So when BMS's SOC calibration is triggered, these SOC estimations are corrected and to provide the precise indication of the SOC. So PPC should be able to enable a single or group of units, enable this calibration mode automatically so that the cell balancing happens and the SOC is corrected, while other units are meeting the market obligations. And in fact, even the unit that is getting calibrated and balanced is also available if needed to meet the market obligations. So that is the key. We don't have to take these units away from the market, or we don't have to, but they are available there doing this automatic calibration and the balancing. But if this really the plant needs to meet the market obligations, these units are needed, we can bring them back in. So from the screenshot here, you can see that the unit 2 is put automatically into the SOC calibration there. And at the end of the calibration, you can see a dip in the SOC. That is where the SOC correction is happening. It's almost like 4 to 5% there, and which is not negligible. And that's how, with this feature of automated feature of SOC balancing, a unit could be calibrated. So without this auto steering, customer operator needs to manually put these units, go through all these steps to calibrate them and to balance the cells manually. And then you can imagine how much effort and expensive it could be for large scale utility sites, right? To gain the benefit of well-balanced and regularly calibrated site. So with this feature, all this process happens automatically without customers worrying about calibration and balancing of the batteries. So what a relief that this particular automated feature gives to the customers. Next slide, please. So what else can a sophisticated bus power plant controller do? These days we talk about multi-gigawatt hour size best sites, not 100 megawatt anymore, 200 megawatt anymore, multi-gigawatt. So that means the best PPC need to scale to support these multi-gigawatt hour size sites. And also some utility customers like their site or the plant to be islanded when the grid connection is lost. Of course, utilizing the grid farming capable inverters, and if there are any co-located renewables to support the load while the plant is disconnected from the grid. And when it connects back to the grid, they want the site or the plant to go back into the on-grid mode. So this transition between on-grid and off-grid states is another important feature that some utility customers might want to have, and the best PPC should be able to support that. And of course, the best PPC should be able to do the closed loop control or open loop control as needed. And in some markets, also it should respond to the frequency changes very fast. So, I mean, a best PPC is not just a best controller, but where it is a sophisticated power plant controller that could do all these, advanced features. So at this point, I would like to hand it over to my colleague Scott, who is from our delivery and lifecycle organization, to discuss a bit more about on key markets and the closed loop control and fast response time requirements from these dynamic markets. Scott?
Thanks, Sunitha. Hi, everybody. In this next section, I'll draw on Wärtsilä's experience delivering power plants around the world. I'll show how some of these advanced functions help the power plants remain competitive in both current and the emerging markets, while also remaining grid code compliant. So during the last few years, we've seen rapid growth and significant change, and I think we can all agree there's no sign of this trend slowing down. So across the globe, grid codes and energy markets are also rapidly evolving, primarily managing new renewable heavy landscape of generation. And the PPC is one of, if not the most important piece of equipment when it comes to being able to comply with grid code and participate in the most lucrative markets. So on this slide, I'm showing a bit of a sliding scale of complexity for grid code and markets. And if we start from the left side, we have large stable grids with firm baseload power that may only really need a BESS to participate in a wholesale energy market, which would be following a signal from a central dispatch without doing too much extra processing. The next level of complexity involves providing ancillary services. Primarily, those are going to be frequency or voltage support, and those would require the PPC to react to a local measurement of grid conditions. Moving further to the right, we get into fast frequency response, which is typically going to be 250 milliseconds or so, and grid forming capabilities, which include virtual inertia and short circuit contribution. Now, in recent years, ERCOT in Texas, AMO in Australia, and National Grid in the United Kingdom have proven to be pretty good indicators of how batteries can support grid stability when transitioning towards primarily inverter-based renewable generation, such as solar, wind, and batteries, mostly transitioning off of fossil fuels and those larger central dispatched assets. And now as renewable penetration increases in these other markets, the demand for fast frequency and grid forming functions is almost certainly going to follow. Next slide, please. So now to talk a little bit about the closed loop control, whether the plant is following a signal in a wholesale market or responding to local measurements and frequency markets or performing grid forming functions, the PPC has to be able to maintain accurate power at the point of interconnection. If the plant is not achieving the expected power output, there'll likely be negative impact to revenue, potential penalties for either not complying with local grid code or the market rules. And now the most reliable method for ensuring an accurate response is a properly tuned closed loop controller. And typically that's going to be using a PID. And on this slide, I have the general process for a closed loop controller. So just in case you're not familiar with that, if we start on the measure part of the process, a power meter or a transducer is used to measure the power, usually at the point of grid connection. You could also call it the point of measurement, which is the point at which we're trying to achieve a target power. Then the controller adjusts the power set point for the BESS based on the error between the measurement and that desired target power. Then the PPC distributes that total power among all of the PCSs using some amount of power allocation algorithms. And then each PCS delivers the requested power that came out of that distribution. And now this cycle repeats continuously, and each iteration of the process happens, 10 or more times a second. Next slide. Okay, so to highlight the benefits of why we would want to use a closed loop controller, we'll walk through a short real world example. So consider the BESS plant on the left with a power rating of 100 megawatts, like a nameplate power, and 25 PCSs or ESS units. Now the plant is following a 50 megawatt dispatch signal from the central dispatch. So that's about 2 megawatts for each unit. When one of the PCSs trips offline due to a ground fault or some other fault. Now, as this PCS trips, the power at the point of interconnection, that meter at the top, would drop by roughly 2 megawatts, whatever the power that unit was providing. In the next iteration of the measure phase of that closed loop controller, it will detect that new 2 megawatt error. So in this case, dropping to 48 megawatts instead of 50 megawatts. So in the adjust phase, the controller increases the demand to the remaining 24 inverters to account for that drop in power. So that as a result, the plant very quickly returns to that 50 megawatt dispatch power level, and the grid barely sees any change. I mean, this is happening so fast that the power just comes right back up almost immediately. Now, that PCS gets worked on, gets maintained. Now, when it's returned to service, while the site is still, let's assume the site is still following that same signal. When the PCS is returned to service, the power demand and allocation will adjust again to keep the overall power consistent. So when that new unit comes on, it can take some of the power distribution. So the other units kind of ramp down while that first one ramps back up. And then if we continue with this same example and assume during that outage period, if those batteries are now 10% higher in SOC than the rest of the other 24 units, this is where an SOC balancing type power allocation, like the one Sunitha was talking about, would come in and allocate a larger portion of that discharge demand to that unit 1 to drive its SOC back down to the SOC of the other units. So you kind of see more power coming out of one unit because it's at a higher SOC. And then that will drive the SOCs back to that balanced level. Okay, next slide. Okay, so now we're going to take a closer look at what it takes for a plant to successfully participate in one of these fast frequency markets. In this case, we'll consider a response time requirement of 250 milliseconds. And in this example, we'll consider a plant using separate PPC and BESS controller hardware provided by separate vendors. The process starts at T0 on the left, with the PPC receiving a frequency signal over the local network, usually from a meter located at the point of interconnection. So this is a measurement of the actual grid frequency as seen by that meter. Next, at T1, the PPC processes the signal, adds power from any other markets that it's participating in that stacked operation, and adjusts based on the closed loop control feedback. At T2, the total calculated set point is then sent to the BESS controller over the local network based on some interface agreed upon by the two controls vendors, between the PPC vendor and the BESS controller vendor. At T3, that BESS controller receives its target from the PPC, processes the signal, applies its algorithm to distribute the power across the units, and then transmits a set point to each PCS in each of those units. And then finally, at T4, each PCS begins to respond and ramps up to the target power level. So with the rough estimates that are on the slide here, the worst case is about 260 milliseconds, which is larger than 250. So obviously it's critical for this process to be properly optimized, and any little bit of time savings goes a long way. Next slide. So here's the same process, but in this case, we're looking at a plant that's using an integrated PPC and BESS controller solution. So in this case, there's only one set of hardware and software that is performing both the PPC layer and the BESS controller layer functions. So in this case, no external network interface is required to transmit that BESS target. So with all else being equal, removing just that extra hop between controllers brings our worst case closer to 240 milliseconds. Still a tight margin, but it is bringing you closer to 250. Now, aside from the speed implications, removing that interface also simplifies commissioning, operation, maintenance, takes kind of one extra step out of communication and collaboration, and having to have another interface line up just perfectly. Now, advanced PPC solutions will go even further. They'll take advantage of modern software architecture to further reduce time that it takes to process signals, calculate responses, and transmit commands to, on gigawatt-hour size sites, tens or hundreds of PCSs simultaneously. On gigawatt-hour sites, we're talking, hundreds of PCSs. Okay, next slide. All right, and finally, I'd like to highlight the impact a high-performing PPC can have on the success of a real large BESS. So in this picture, we have a 250 megawatt battery. It's located in Australia, and it began commercial operation in the second half of 2023. Now, as mentioned earlier, AMO has introduced new markets to utilize unique capabilities of a BESS. Most notably is the very fast FCAS frequency response market. Now, to participate in this market, an asset must deliver its contracted power within 250 milliseconds of a contingency event. A contingency event is when the frequency changes outside of a deadband, so you can think of it like a significant frequency change. It's usually going to be triggered by some other plant tripping offline, either a load or a generator. And the PPC must leverage high-speed measurements, closed-loop controls, and efficient power allocation to accurately and reliably respond to these grid disturbances. The financial success of this plant, which I have highlighted on the slide there, has been in part driven by this very fast FCAS, specifically the RAISE market, where you're exporting power. With this one plant providing about 15% of the total national demand for this service in Australia. Part of that is because less than 10% of the assets that are participating in that national electricity market are actually able to deliver the very fast FCAS RAISE service. As a result of those facts, the energy prices in that market are currently around 6 times higher than the fast FCAS RAISE market, which has a 6-second response time requirement. So just stepping kind of one tier down into a slower response category, you see a 6-fold change in energy prices. Okay, next slide. So this is just to wrap up the presentation. I'll review what we've covered and key takeaways we'd like to leave you with. First, we described the general layout of the generating equipment, hardware, and software systems that exist in a typical battery energy storage system. We defined a number of terms such as BMS, BESS controller, PPC cloud apps, and highlighted that the use of the term EMS can be kind of ambiguous, not really giving you an accurate representation of what a given system can actually do and what it's even expected to provide. So using more specific terms like PPC or BESS controller, or just asking more targeted questions about what a proposed EMS can and will do can help avoid costly surprises during project execution. Second, we covered the specific components and features of a complete EMS ecosystem and how those can unlock value in a BESS, either by themselves or as part of a larger whole. For instance, cloud-hosted optimization apps can forecast load and prices to bid into a market or fulfill PPA commitments. Data analytics can ingest immense quantities of data and generate actionable insights. Stacking power operations allows participation in multiple markets simultaneously, and power allocation algorithms can unlock additional capacity by automatically steering batteries to a condition that triggers the SOC calibration within a BMS. Third, we highlighted how critical it is for the components of an EMS ecosystem to be built using modern software architecture principles. The software components need to be scalable to manage the thousands of devices on gigawatt-hour sized sites. They need to be maintainable and extensible to evolve with changes in grid code and market requirements. And they need to be pluggable to support equipment such as inverters, batteries, thermal management systems, and SCADA systems from a wide range of vendors. Finally, we reviewed how grids and markets have been evolving, primarily as a result of an increased share of the power generation coming from inverter-based resources, such as solar and wind and batteries. And the recent changes to requirements in markets like ERCOT, the UK, and Australia have been pretty good indicators of what new requirements we should expect to be seen pop up elsewhere, especially as renewable penetration increases, worldwide. So that brings us to the end of the presentation. Thanks for your time and attention. Take a few minutes for Q&A.
Thanks, Scott. Thanks, Sunitha. We have a few questions so far. Please be thinking about some more as we start to answer these. Some of them are, I think, a little. We'll have quicker answers for them. Others are going to require a bit of a lengthier response. Just looking chronologically as they were asked, let's kind of go a little bit in that order. So Scott and Sunitha, I'll take the first question, and if you want to add anything to it, feel free. And then I don't know which one of you would like to answer maybe the second question there that's in the chat. But so the first one from Javier, thanks for the question. What element is used to automatically balance cells within the BESS? Is it the BESS controller or only software or also hardware? So it's interesting. Let me go back actually to slide 8 here. We don't depict the BMS on this slide, but there's a BMS on it. There's module level BMSs, there's the rack BMS, and then you have sort of the BESS controller and then the power plant. The BMS is the one that's actually doing the balancing, and whether it's a passive or an active balancing system would dictate what kind of hardware is there. So a passive balancer is a resistor, so you're bleeding off extra energy in one set of cells to bring them into alignment with the others. The part that gets a little tricky in these modern massive utility scale plants is that there have to be certain conditions, depends on the BMS and what that's designed for, to then trigger the balancing. So it often doesn't just happen all on its own all the time. So sort of like active continuous balancing, often you have to have the SOC at some level for a certain period of time to trigger that balancing. And then when you have multiple units, this gets a little bit into Luis's question. So when it comes to the SOC calibration work, there's a lot of different ways that this could go, but let me describe for you what we're seeing emerging and what the market is really demanding, and that a modern EMS platform should be able to provide for you, but that a standalone only BESS controller might not be able to provide for you. So if you have access to things in the cloud. If there's some analytics app that can keep track of which units have been balanced when, and which units might need to be balanced more, while some calculations can happen here, really optimizing the scheduling of those and making sure that you have a fully automated system that's acting in a supervisory way to keep track of all of that kind of requires this kind of ecosystem. And so there are a lot of different pieces of the puzzle in terms of how do your vendors plan to provide a balanced system continuously. And so Luis's question goes into, there's some aspects there. He asks, how does the SOC calibration work with respect to the rest of the power plant? Do you need to have all the best units charging in order to measure the calibrating unit? So no, depending on how long it's been since calibration, units in a modern EMS should be arbitrarily and or hierarchically selected for calibration in an opportunistic way. So this happens if the calibration should happen when the SOC is low. You want to have automation that will shuffle the energy around. So having one unit getting driven low, Sunitha had a slide, I think it was 15, this one. So having a unit get driven down low and resting and then getting put back up into the group, that can happen opportunistically, unit by unit, when units are low. And if it's not happening in an intelligent manner, if it's just happening on a clock, or if it's happening on some predetermined schedule, you'll have to shuffle a lot more energy around within the plant, because as Scott described, the plant is in the market delivering power, and you're just taking a couple of units to do this calibration. You're shuffling energy around. We're intentionally moving the SOCs away from each other with automation to get this calibration to happen, and then pulling everything back into the mix. And so optimizing that is where some of the cloud components really come into play.
And I think Javier's question also has, is it only software or also hardware? Yeah, it's a software.
But it's software on multiple levels. So there's
software on multiple levels. And I think balancing, again, the purpose of this session is to talk about EMS as a confusing term. I think keeping SOC balanced across units, keeping SOCs balanced within a unit, and then doing SOC calibration, those are all different topics. And so it's important to do some learning about these different pieces and how they interact as well.
I wanted to add just one bit of context to that is, when we talk about calibration, specifically calibration, it really depends on the chemistry of the battery and then also the specific vendor's BMS. But generally the concept is, whenever power is moving, so when there's current coming out of or into the batteries, you can't actually measure the SOC accurately. You can estimate it. You can guess, okay, I've had a certain amount of current go away. I can, base my estimation based on that, but there's going to be error. So what calibration really means is that we're putting the battery into a spot on its resting voltage curve where you'll actually be able to see differences in the amount of energy based on the voltage. And then we're letting it rest. So the EMS needs to let that unit rest so that all the voltages kind of settle down to where they where they are in a true resting state. And then the BMS can look at that and say, well, this voltage is higher, it has more energy. This voltage is lower, it has less energy. And then it can build its balancing plan based on that. That's really what calibration is. It's just putting the BMS in a place where it can do kind of a diagnostic and figure out what it needs to do next. And then return it to service, and it will do whatever it needs to do to achieve that balancing plan. But really, where the EMS level comes in is orchestrating all of that throughout the whole plant, because like Luke is saying. I have to discharge this unit to get it to where it needs to be, but I'm not in a market that's letting me discharge, so I got to absorb it into other batteries. Like all of that orchestration has to be done at like a PPC level.
Yeah. Okay. Sunitha, thanks, Scott. That was really good additional there. Sunitha, can you maybe respond to Ivan's question? So which could be a reason for having manual control of a battery SoC in a BESS system? So why would somebody do something manual? It's related to the automation we're talking about too.
Right. I mean, in general, normally we may not need to do that, but if the unit probably like has some kind of a repair, for example, and it was gone, it was not in operating mode for a certain time. Now its SoC is like deviating from others, and it is in the manual control mode. And while repairing it, probably they want to test it and see, and then they want to bring it back where it is. So that is where it would manually will be controlled. But otherwise, when the plant is in the auto operations in the market, normally it will not be, manually controlled.
Yeah, thanks. I want to respond to Fernando's question just in brief, because it's probably a question that others have. I'm not seeing upvotes necessarily for it, but how is response time affected by using string inverters in a large size project? How can it be minimized? I think the only thing I would say to this is just, it is definitely a harder problem. There's a lot going on. If you don't have the most modern state-of-the-art controls platforms, you will not be able to achieve the fast response times that the most lucrative markets demand. It's a problem that the world is working on this problem in a few different contexts. I think there's lots of companies who sell a string inverter based product, and I think there are efforts to keep those response times as low as possible, to keep these plants as responsive as possible. But it is a harder problem, and minimizing the number of hops, as Scott described, there's all kinds of strategies there. But in the end, you have to have some pretty coordinated and powerful computational things happening to get that to happen effectively. I don't know, Scott, if you would add anything else on that topic.
I think you hit it. You're sort of, I guess the answer is it depends. You are very likely going to add an extra layer of distribution. So instead of an ESS unit being one central inverter with one set point, you're likely having like an abstraction virtual ESS unit that then has to distribute between each string inverter. So that's going to add some time. If there's extra communication levels in that same abstraction, that could add some time. Now, maybe the string inverters would actually turn out to be faster than the central inverter. So maybe you kind of gain some there. So it's hard to give a good answer other than it really depends. Just like it depends on who's providing a central inverter and what response time it can achieve.
Yeah. Even central inverters have a pretty wide variation in capability. Yeah, 100%. Let's Mateus's question, Sunitha, maybe you could respond to just a little bit in just what we're used to. How long does it take for us to integrate a new battery vendor? Let's assume they meet our requirements, but there's driver development, there's testing, there's a bunch of things we do.
Right.
Rough estimates.
Yeah, from our experience, it normally takes even the collaboration time with the vendor to understand how their BMSs work and what sort of structure they have, what kind of protocol, all that. So that collaboration takes some time, and then we kind of once we understand all that, and then we have the interface documentation nailed down, then it would probably take around a week to develop the driver. And then, of course, we have to go back and do the factory acceptance test with the vendor, and so on and so forth. So yeah, it's just not developing the driver the first time if you are integrating with the vendor, right? I mean, there is a lot of collaboration. There is a lot of, I mean, sometimes even a kind of negotiation on the registers and on the how the certain commands are exposed and not exposed, the data that PPC needs, whether it's coming in or not coming in. So that collaboration takes time, and then the driver development, and then we have to go and test it with the vendor's equipment directly using the driver.
Yeah, I think it's fair to say, Sunitha, you can
Yeah.
agree or disagree that where we are right now as an industry, we're not at a point where we can just take a manual, walk away, and come back with a perfectly working driver. There's still too much variation and kind of like a lack of standard implementations to be able to do that. I think we will get to that point, but right now it still requires a lot of collaboration.
Collaboration with the vendor,
yeah.
yes.
Yeah, so we're reaching time here. I want to be respectful of everybody's time. If you have to drop off, really thanks for being here. There are a few more questions in the chat. At a high level, Greg, your question, I mean, we are not BMS experts here. I think there's a lot of other good learning materials out there on BMS in general. It's taken us a lot of time to understand how all the different pieces of a BMS. I don't know if there's a specific one I would say was more challenging or harder than others, but some things took us a while, each individually to learn.
I'd say my quick answer is SOC calibration.
Yeah, that's the big one. Carlos has a couple questions there. I would say a power plant controller should really ensure that if there's power flow restrictions at the point of interconnection or measurement, that those are adhered. There's a lot of regional specifics. So it's not entirely clear to me what item 1 in your question is, if it's a DC coupled plant or an AC coupled plant, but if you want to restrict charging from the grid to only charging from the PV, for example, then that normally sits inside the power plant control level. And cybersecurity is a huge topic.
Sorry, just on number 1. Yeah, I think the way to think about it is that ultimately control of the POI power is always going to be the PPC.
Yep, exactly. Cybersecurity is a huge topic. You should really we should run entire webinars based on that. But there are standards like the IEC 62443 certification for power plant controllers, which really ensures that not only the equipment itself is as cybersecurity as possible, but also that the software development itself is also done in a cyber secure manner, that you can't have rogue software developers injecting code and deploying to sites and things like that is all kept track of. Eduardo, your question on scope. On our side, because we have in Wärtsilä an integrated PPC, BESS controller, and cloud ecosystem, we take on all of the scope. I think it's very normal for BESS for battery providers to just have the BESS controller and not even provide a power plant controller. So there can be a wide spectrum of scope depending on what suppliers are offering, and it's really up to you as the shopper in your RFP process to require everything that you need. And if certain vendors can't supply that, they'll have to respond, can't supply this, can't supply that, and so on. And then you'll know, and then you can procure those pieces of the puzzle elsewhere if that's what you need to do. And then just the final question in the chat. The scope, Nacho, that you're asking about really normally resides in like some kind of automated bidding solution or an energy trading platform, which is really in the cloud only. That's in the cloud apps section almost certainly every time. That's not something that's happening on the site. So I think we got through all of those questions. Thanks everybody for your time. And